Hello and welcome back. We are solving a kinetics rigid body problem involving friction, where we have a spool that's rolling on a rail and is being pulled down with P, which causes it to spin in this direction. We determined in the last video where we set it up that we would need two cases for this problem because we are not sure if it is slipping or not. This video is going to be solving our first case, case 1. Case 1, we are making the assumption that there's going to be no slipping. So this video will be for case 1. No slipping. Okay, and we also determined in the last video that what that means to us is that it's almost like there are gears that are interlocked in the space between where this drum rolls on the rail. The drum does not slip on the rail. So that means we have a direct relationship between the acceleration of the center of mass and alpha, how fast it's spinning. That relationship, as we know from kinematics, is that AGX is equal to alpha r, and in this case we need a negative sign because if we look at my positive x direction, a positive alpha would cause a negative x movement, so we need that negative sign there. We also determined that we need to check if our assumption is right at the end of the problem. And what are we going to check? We're going to check that friction works, that our friction is going to be less than or equal to the maximum friction, which is static friction, mu s times n. Okay, so that's what we're going to be working on in this problem, is case 1, no slipping. How do we do that? Well, I have moved our free body diagram and our kinetic diagram up here so we can use them both. The only thing I've added is I added the distances, the radii. We've got 0.15 meters is the inside radius, 0.3 meters is the outside radius. So we have that information. And what we're going to do is we're going to use our kinetic diagram. We're going to use what's called kinetic moments. How kinetic moments work is we're just going to say the sum of the moments about any given point. In this case, I want to choose point A, which is at the bottom where the spool meets the rail. The sum of the moments about point A, and by the way, you could pick other points. You could pick this point over here. You could pick G. All of them are going to lead to the correct answer. This is where you can bring in the knowledge you learned in statics, where if you choose a point where a lot of forces are passing through, there's not very many moments involved. And I'll show you that in just a second. Some of the moments about point A are going to be equal to the sum of the kinetic moments. This is that funny looking M that they use in the textbook about point A. Okay, basically all that means is we're going to look at this as if it as a free body diagram, and we're going to find the moments about that point. Then we're going to look at this kinetic diagram as if it was a free body diagram and as if these pseudo forces were actual forces. Think of it as an equivalent system. These forces are causing this motion. These are equivalent to each other. We're going to look at them in the same way. Okay, so some of the moments about point A. We see F, N, and W. The line of action of all three of those forces pass through point A, meaning they're not causing any moment about point A. The only moment will be caused by P. If I put my thumb on A, point my fingers towards P, it would tend to curl my fingers in my right hand, which means it's a positive moment. So we're going to have P times the distance between A and P, this distance here, which is 0.3 meters. That's the full moment on the left-hand side. The right-hand side, we do exactly the same thing. It's going to be equal to, you notice the line of action of the acceleration of A pseudo force goes right through A. So in that case, it would not cause a moment. We also know that that's 0, because we're not going to have any acceleration in the y direction. So there's two reasons why that force doesn't come into our equation. However, the pseudo force mass times acceleration of the center of mass in the x direction does come into play. If I put my thumb on A, point my fingers towards that force, it would tend to bend my fingers backwards, which is a negative moment. That's the pseudo force. Now I multiply it by the distance. What's the distance? Well, it's the distance between A and G. And you can see that distance over here is the radius of the inner circle of 0.15 meters. Okay? And of course, we have to add on our couple moment, the IG alpha, just like any couple moment. We add that on when we're calculating moment. There's our equation. Now if we look at our knowns and unknowns, P is given, so that is known. M, we know. AGX is not known. IG we can find. and alpha is unknown. So we really only have two unknowns and this one equation. So we're getting close. Our unknowns are here and here. Okay, let's go ahead and calculate IG. And for this, we have to remember the definition of radius of gyration. The definition of radius of gyration is that there's a direct connection between moment of inertia and radius of gyration. The moment of inertia about any point is going to be equal to mass of that object times the radius of gyration about the same point squared. Okay, so we are given the radius of gyration of 0.2. So for us, IG is going to be equal to 100 kilograms times 0.2 squared. And that's in meters, so that would be equal to 4 kilogram meters squared. Okay. So we have our IG. It's equal to 4 kilogram meters squared. Just going to reclaim a little bit of space here. That's going to fit in here. We're going to plug in our mass. We're going to plug in our P. Plug in our P. P is equal to 500. 500 times 0.3 is 150. So 150 Newton meters is equal to negative. The mass is 100. 0.15. We get negative 15 times AGX plus 4 alpha. And now you can clearly see we have an equation with just two unknowns, AGX and alpha. And this is when we go to our case and we say, well, our case 1 says no slipping, and we know if there is no slipping, our AGX is going to be equal to negative alpha r. I'm going to go ahead and solve for AGX first, so I'm going to rearrange this and say that I know alpha is equal to negative AGX over r. And what's r? The inner radius, 0.15. So that's equal to negative AGX over 0.15 meters. Plug that in for alpha right here, and we'll get 150 Newton meters equals negative 15 AGX plus, I'm sorry, there's a minus because we're bringing in that negative there, minus 4 AGX over 0.15. We can now solve for AGX. It's equal to negative 150 over these two added together, which ends up being 41 2/3. Okay, that's equal to negative 3.6. And we're in meters per second squared. Okay, we have found our AGX. In order to find our alpha, we just go up to this equation right here, and we say alpha is equal to negative AGX, which is negative 3.6, over 0.15, which is going to be equal to 24 radians per second squared. Okay. Let's do a sanity check. We have a positive alpha. That means that we are rolling in this direction using my right-hand rule. And rolling in that direction is giving us a negative AGX. In other words, the center of mass is moving in the negative x direction. Okay, that seems to work. So do we just box our answer and walk away? That would be nice, but we need to check that our assumption was correct. Okay, that's the next step. To check our assumption is correct, we need to figure out if frictional force is less than or equal to mu s times n. We didn't solve for frictional force over here because it wasn't necessary to find what we were looking for. So let's do it now. We're going to solve for frictional force. We'll just say sum of the forces in the x equal mass times acceleration in the x direction. That's one of our kinetic equations of motion. If we look at our free body diagram, some of the forces in the x direction, there's only friction. It's in the negative x direction. So we end up with negative F is equal to our mass, which is 100 kilograms, times our acceleration, which we just solved for, is negative 3.6 meters per second squared. Okay, we multiply those together, we get 360. The negative signs cancel out. So F equals 360 newtons. we know what our frictional force is, 360 newtons. However, we don't know if that's above our maximum allowed frictional force. If you remember, how friction works is when you start trying to get two surfaces to slip in relationship to each other, the friction will just match whatever force is there until it hits a certain point. Oh, I went a little too high for the board. Hold on just a sec. So as you start ramping up your friction, friction matches until it gets to a certain point, and then it drops down and does kinetic friction. Our axes on this graph would be load versus frictional force. And what we have to check is if we're in this area down here. If we're in this area, that means that our friction is less than the maximum friction, and the maximum friction is mu s times n. So that's what we got to figure out next, is mu s times n. And to do that, we'll use sum of the forces in the y equals mass times acceleration of the center of mass in the y. Now we know that the center of mass is only moving in the x, so this is 0. And we have our sum of the forces in the y. We have p, n, and w. So we'll have negative p minus w plus n equals 0. The pluses and minuses are just whether it's positive or negative y. Solve for n. N is going to be equal to p plus w. Both givens, that's going to be equal to 500 newtons plus our w is mass times gravity would be 100 kilograms times 9.81 meters per second squared. Okay, so that ends up being 981 plus 500. So our normal force is equal to 1481 newtons. Now we need to check what is our maximum frictional force that the friction between these two surfaces will allow. That's our static friction. Static friction is equal to mu s times n. Mu s is given as 0.2, n is 1481, so that's going to be equal to 0.2 times 1481 newtons. And if we do the calculation, that'll equal 296.2 newtons. Now is when we step back and think. We need 360 newtons of force. We need friction at 360 newtons of force to keep these from slipping. However, the maximum friction allowed is 296.2 newtons. What does that mean? Well, it means that we've gone up and above this graph, that we've continued up, and that our assumption is invalid. It means that there is slipping because our frictional force is greater than mu s times n. If that's the case, we know that these two surfaces would actually slip in relationship to each other. And we can cross out case 1 as a bad assumption. We can draw a sad face because we have to keep solving the problem. In the next video, I will be solving for case 2, where the assumption is slipping. And we should be getting a different AGX and a different alpha. We expect our alpha to be larger because the slipping is going to allow it to accelerate, to have a larger angular acceleration.